All right, we're going to start chapter 14, section 1, and we've got, we're going to do half-life, okay? So what we have half-life is a species, is the time it takes for half of the amount to disappear. And this, well, react. Let's go with react. Most of the time you think about half-life with respect to nuclear decays and stuff like that. But in chemistry, it can be anything associated with any reaction at all. So it's going to change. Now, half-life comes in a variety of forms, but the one that's most important is the first order, because first order is the most common reaction we have. So here is our first order reaction. However, you can rearrange it, and so you will have this form on your formula sheet, but I'm going to show you how to rearrange it. If you move the natural log to the other side and subtract it for natural log rules, and you can review this if you want. If not, take my word for it. I had to look it up. So if you subtract two natural logs or two logs, then that becomes a division of the natural logs is equal to minus KT. This form is also very, very, very common. So this is actually the form I typically use. So at the half-life, and we specify it as T1 half, then the concentration of A sub T is equal to half the concentration of it originally. Okay, so what we're doing is we're relating the concentration of the compound at the half-life. So then that means that if we plug that in, then we get 0.5 of A sub O over A sub O, forgot my natural log, is equal to, whoops, looking at the wrong thing, is minus KT. So if you take the natural log of 0.5 is equal to minus KT, then that actually comes out to 0.693 approximately. So T1 half, that's the time half-life, is equal to 0.693 divided by K. So if you'll notice, for half-lives of first order reactions and first order reactions only, okay, first order is independent of concentration. Now, that is unique to first order. If we look at second order, and I pulled the slide, y'all should have it, but if you look at the rates for zero order and second order, they are both concentration dependent. The only one that is not is first order. Okay, so, and those are the most common. So when we work on, and we'll work a second order, I think, later, I will pull the equations off the sheet. Okay, so here's our first problem. If the rate constant for composition of aqueous, was found to be. Okay, so K is our rate constant, so that's 1.6 times 10 to the minus 3 minutes to the minus 1. The reaction gave a linear first order plot. That is a long way of saying it's first order. Okay, so what is the half-life? Well, the half-life, we said, was 0.693 divided by K. So if we plug that in, that's 0.693 divided by 1.06 times 10 to the minus 3, which when we do the math on that, we get T 1/2 is equal to 653.77358. Now, if we stick to, and the minutes came to the top, so 653.7736 minutes. Okay? On this one, I have to keep 4 places after the decimal. Now, for some bizarre reason, I won't say bizarre because I'm bizarre. For some reason, people like to change the units. So if I don't specify, oh wait, I specified, see, bizarre. Okay, so in this one, I could have left it at minutes, but if I convert it to seconds, it's 39226.414 seconds is my half-life. Now, does it matter which one I leave it in? No. If I don't specify, make your life easier, keep the simplest one. If I specify, convert it to whatever. I could have easily converted it to hours, and it's about 10 hours. I can't see, I didn't put all the details in. So about 10 hours. Does it matter? No, as long as you keep a unit that is correct. Now, then it says how long would it take the reaction to be 67.5% complete. So that means that we're looking at A sub T. And we need it to be 67.5% complete. That means that if we look at it, that means that only 32.5% is left. And the trick is that's the part we need to put into our equation. So what we're saying is it is at time t, which we don't know what it is, then we have 0.325 of whatever we started with. Remember, A sub O is the original, times 0. So that's the original amount. So that's what we know. So we go back to our formula, which is the natural log of A sub T over A sub O is equal to minus K sub T. I shouldn't say O is 0. A sub 0. Okay, so we have natural log of 0.325 A sub 0 divided by A sub 0 is equal to minus. Now, here I didn't specify. So, actually, I'm not looking for the half-life. It's up here. So, this is your K, which was given, times 10 to the minus 3 minutes to the minus 1 times T. Alright, so if we do the math, we get negative 1.12393 is equal to negative 1.06. Be careful to not drop the negative, because you should always end up with a positive time. So then we'll divide both sides by the negative K, and we end up with time is equal to 1060.3114 minutes. Okay. If you wanted to convert that, that's fine, leaving it right there. Whoops. No, it's not if I change the number. It's fine to leave it in minutes, but if you wanted, you could divide it by 60 and get 17.6719 hours. Then you could divide it by 24 hours and get 0.7363 days. Now, why did I do that? Because, okay. The reason why is watch your units, because especially on D2L, if I'm hand grading and I'm expecting the answer in minutes and you give it to me in hours or days, I can see what you did on D2L. Look for the unit asked for, because in case you haven't figured it out now, there's no mercy when you're dealing with an electronic grading source. So, and that's why you give me the submission so I can go back and look at them, which I'm working on constantly as tests and quizzes come in. All right, let's look another one. This is a half-life. So in this particular case, we are actually given the half-life, not the rate constant. Okay, and we're asked for what the rate constant is. So T1/2 is equal to 0.693 divided by K. So K then is equal to 0.693 divided by the half-life, which is equal to 0.693 divided by 62 seconds, which gives us 0.01117749194 seconds to the minus 1. Now, for simplicity's sake, we'll keep up with, 4 places after the decimal. 4 significant digits after the decimal. Okay, so here is my K. All right, so we're good on that part. Then it's required for time required for 40% of the phosphine to be left. That means that at the unknown time, we are left with 0.44 of whatever we started with at time 0. So notice that on this one, we said that it's 67.5% complete. That means we had to subtract it. On this one, we are left because we're always looking for the amount we have present left. So we're back to natural log of concentration at time divided by the concentration of 0 is equal to minus KT. So now we have the natural log of 0.44 A sub 0 over A sub 0. So those cancel, is equal to minus 0.01118 seconds to the minus 1 times our missing time. So we end up with the natural log of 0.44. And again, you don't have to write, forgot one, each of these steps, but whatever floats your boat. So we end up with minus 0.71334. And I don't write this down. I've written a few more digits, but I'll let my calculator carry it when I'm doing the math. So when we finish the division, we end up with the time is equal to 63.805893 seconds, which, if we're keeping 4 decimal places, 63.8059 seconds. Now, on problems like this, I tend to keep 2 seconds or 1 second, and I'll tell you, I'll be specific. Again, significant figures are incredibly important. However, when we're playing with numbers this small, it starts to get really, really ugly, because if you only have one significant figure, it's 60. If you have 2, it's 63, actually 64. But on the scale of what you're measuring, you can get a variety of answers. Okay, so here's the next one, the half-life of reaction. How long will it take? Now, on this particular problem, what we're looking at is the order is changing. Okay, so if you'll notice, this is A and this is B. So we're flipping back and forth, because the first one's going to be first order. We're told the half-life, okay, so T1/2 is equal to 15.8 minutes. Initial concentration is A. So A sub O, A times 0, initial is 0.340 molar. How long will it take the concentration to drop? And so we're looking for the time. So what we have is, remember, the natural log of A sub t over A sub 0 is equal to minus KT. So we have a sub t, we have a sub 0. We're looking for t. We got to find k. So if we come back over here, remember, k was equal to 0.693 divided by t1 half. So if we substitute in the t1 half, we end up with k equal to 0.0438676 minutes to the minus 1. Again, I would leave that in my calculator and let it run. But over here we have the natural log of 0.0740 molar divided by 0.340 molar is equal to minus 0.04386 t, using 4 significant figures. So we find out that this is the natural log of 0.217647. Now, I'm not going to lie. I understand order of operations, and I understand my calculator in order of operations, but I hate parentheses. So I always put in the two amounts, run that, and then take the natural log of it. But you can do whatever way makes you happy. So we end up with negative 248805. Again, I'm going to let my calculator carry that. So I'm writing more digits down than I would normally, just because I would not even be writing this down. If I was you, I would be writing down certain things, like I would be writing down this step, but I wouldn't be writing down the next step. Okay, so your time is equal to 38.77 minutes if we were doing 2 places after the decimal. So there's our time for the decay for first order. Now watch what happens if we do second order. Okay, so this is still t1 half is still 15.8 minutes. And this is still a sub 0. And this is still a sub t. But now we're told this is second order. So that's a totally different set of rules. So t1 half for second order is 1 over k a sub o. A sub 0. So that means it is 15.8 minutes is equal to 1 divided by k divided by 0.340 molar. So you have 5.372 is equal to 1 over k. So k is equal to 0.18615 04, etc. minutes to the minus 1. So it's 0.1861 minutes to the minus 1 is the k we're going to use. Okay, and when I did math, I added a 5 on for some bizarre, I kept the 5 for some bizarre reason. Okay, so that's the first part. Then the second part says that how long will time take? Well, for this one, for second order, and remember this is second order, it's 1 over a sub t is equal to k, is equal to kt plus 1 over a initial. So it looks totally very different. So what we have here is 1 over 0.0740 molar is equal to k, which is 0.18615 minutes to the minus 1 times t plus 1 over 0.340 molar. Okay, so you're going to end up with 13.5135 is equal to 0.18615 minutes to the minus 1 t plus 2.9411767. Again, I'd let the calculator carry these digits. So that ends up with 10.572337 is equal to 0.18615 minutes to the minus 1 t. So that means t comes out equal to 56.7947195 minutes, or 56.79 minutes if we're taking 2 places after the decimal. All right, now let's, I do not remember the previous answer, so look, we can toggle back. 38.77, 56. So bottom line is the first order reaction is about half. The time is going to take about a half what it takes with the second order reaction. And is this critical? And the answer is yes and no. What's that mean? It means that you get the number you get, so go with the value that you get and just follow the listing. And I'll tell you whether we're doing a zero order, first order, or second order half-life. It's up to you to identify the appropriate equations. All the equations are on the equation sheet. You saw it on the first exam. Same sheet. So the trick is be able to identify what's what. And I'm not going to lie, on this test you will probably have a real simple problem that is zero order or second order, but you'll only have one, maybe two really small ones. Majority of your half-life, and you will have half-life problems similar to this one and the previous one, where 70% complete or 70% left, and you will be asked to do at least one of those. So be prepared to ID the equations. The last one slide in this section is methyl bromide in the atmosphere. This is one of those little lagniappe informational things. This is actually kind of interesting because this addresses concepts similar to the ozone depletion. And the fact that something that has no effect, inert, on the surface of the earth as you go up in the atmosphere changes drastically its reactivity. So this is kind of cool to read over.